See, there are in general 3 different methods given, general methods given for preparing alcohols. The first method that we talked about was from alkenes. And here we have 3 sub-methods given. So let us talk about the first method that we have here. This is acidic hydration of alkenes. Acidic hydration of alkenes. All right? Okay. So now, if you take any alkene, general alkene, and if you want to perform acidic hydration, you will have to take catalytic amount of acid in water for adding water onto an alkene. Whatever acid you add, it will generally be in form of H3O plus. And the first thing that happens is your alkene would pull one of these hydrogens, and there would be a kind of protonation taking place. We call this as protonation of alkene. This is what we call as the protonation of alkene. The point is, here the pi bond, as it breaks, both the electrons of pi bond would either shift into this carbon to make this carbon negative and the other carbon would become positive, or they can shift into this carbon here, so this carbon would become negative and then this carbon would become positive. Any one would happen. Because there is nothing more given here, right? You know that I can put hydrogen with any carbon and have positive charge on the other carbon. So I'm putting hydrogen here. There's a positive. This is the step number 1, which we call as, this is the step number 1 of the mechanism, which we call as protonation of alkene. Now, protonation would result into an intermediate. What is that intermediate called? A carbocation. No need to say that if there are some substituents here, then the positive charge would remain on that carbon, which makes it more stable, where it is more stabilized. All right? So, this is the first step. In the second step, what we have is this carbocation is attacked by water. Water has a nucleophilic center. What is that? Oxygen. And oxygen would attack this positive center. This would ideally give us an intermediate in which water sticks on to that positive carbon. We call this, as the nucleophilic attack. And once this nucleophilic attack is done, so here I can write nucleophilic addition of water. So there's this nucleophilic addition of water. And now we have the step number 3 coming up. In step number 3, we once again take the same thing. There's this positive charge here. Sorry, I think there were no hydrogens here, so better remove them. We just keep it general. And now we shall have water taking out the hydrogen and giving back lone pair to oxygen. This would result into formation of our product. And H3O plus is regenerated back, which means H3O plus is a catalyst. This step here can be called deprotonation. So ideally there are 3 steps: protonation, nucleophilic addition of water, and then there is deprotonation. Now let us understand the results of all this. The results. What care you have to do. Important things that you have to know here. 1. Addition occurs by Markovnikov addition. Generally, when carbocations are intermediates, it is always Markovnikov, right? So, yeah, most of the times it is Markovnikov. 2. It is anti-addition of water. Pay attention. This is anti-addition of water. You can see that H and OH are on opposite sides. Although it doesn't make any difference here because this bond is able to have free rotation. So it doesn't make any difference here whether I write like this or on the same side, but I just wanted to show you that they have to be on opposite sides as the addition is anti. Now, because this bond rotates, you can even put them on same side, doesn't make any difference. Right? Anti-addition. But when will it make difference? Pay attention. The anti-addition becomes important when I give you a cyclic structure. When I give you a cyclic structure, there is restricted rotation. Now when I put dilute H2SO4, dilute H2SO4 is ideally what? It is basically water and H plus. In which now, if there is anti-addition, how do I put my H and OH is very important. This is a wedge and this is a dash. If one is on wedge, the other has to be on dash. This is how I represent anti-addition. Here, there is restricted rotation, so it makes more sense to draw this, right? Otherwise, there is no sense in doing it. In normal systems like this, where you have free rotation, doesn't make any difference. All right. Now, coming to the next part. It is a very, very poor nucleophile. And it is taken in very, very less proportion. It is hardly any H2SO4. Right? So it doesn't make any difference. All right. Now, what are intermediates? Carbocations are intermediates and hence may undergo rearrangements. Very important, right? So there's something which you have to know here. I'm going to now show you an example where you have rearrangement taking place. Pay attention. Let us take up a substrate like this. All right. This is a substrate, my reactant, and I'm going to put H plus and H, or I may write H3O plus so that it doesn't matter then. It can also be written as H2O and H plus, or dilute acid, anything. The first thing that happens is what? Markovnikov addition. Markovnikov addition goes like this. This is taken up, right? And which of the two carbons do you think will get hydrogen? CH2 with more hydrogens. That's Markovnikov, right? So I will get this. All right. What kind of carbocation is this? What kind of carbon is placed adjacent to that? What is that carbon called? Very good. Benzylic carbon. So if it is a benzylic carbon, where do you think your positive charge would be better? Benzylic. So I have to shift my positive charge on benzylic carbon. How do I do that? Hydride shift. Very good. Hydride shift. So I'm going to have my hydride shift. How do I get my hydride shift? Pay attention. One of the hydrogens would shift here. Okay? So now, what I get here is this CH, CH2 and CH3 and a positive charge here. And now, what is the last step? I am adding water, so plus H2O. And after water gets added, I have to remove minus H plus. So in the end, I would get my benzene ring, CHOH, CH2 and CH3. That's how the product is. All clear? So carbocations are intermediates and you have this. This is also Markovnikov addition, but with rearrangement. So what difference would it make if instead of taking water with acid, I take HX, HCl or HBr? Doesn't make any difference. The first step would still remain the same. First step would still remain the same, H plus addition. Rearrangement would still occur. And in the last step, instead of writing plus H2, I would write plus X minus. That's it. So any such reaction which occurs by forming a carbocation as an intermediate. When will a carbocation become an intermediate? When you have a double bond which has been added by H plus. This is one condition where carbocations are generated as intermediates. I would show you more conditions, but you need to remember how a carbocation in any reaction gets generated. Okay? So this is how it happens. And your product, right? Now, so there were three important things that you have to know about such reactions. Addition occurs by Markovnikov. 2, addition is NT. And 3, because carbocations are intermediates, there can be rearrangement. The fourth thing is, which is applicable to all kinds of addition reactions where H plus is used, right? The fourth and the final most important thing that you have to know is more stable alkenes react faster than less stable alkene. More stable alkenes react faster than the less stable alkenes. What does that mean? It means that, how do you decide the stability of an alkene? I'm giving you 2 alkenes. Pay attention. I'm giving you the structure of 2 alkenes. This is one alkene and this is another alkene. And you have to tell me, how do we decide the stability? By hyperconjugation. Okay, hyperconjugation is because of alpha hydrogens. It is because of what?
Alpha hydrogens.
So where are these alpha hydrogens? The carbon next to a C double bond C. Carbon which is directly connected to C double bond C is an alpha carbon. This is an alpha carbon, this is an alpha carbon. Are these alpha hydrogens? No. They are directly connected. So you cannot call them as alpha. And look at this here. Sorry, alpha hydrogens. 1, 2 and 3 alpha carbons. So where do you think there are more alpha hydrogens? In this case, right? So if this is A and this is P, B has how many hyperconjugative structures? 9. A has how many hyperconjugated structures? 6. And therefore we say, therefore, in above reaction, B reacts faster than A. B reacts faster than A. That is what it means. All okay? HX ऐड करेंगे हाँ हाँ कोई भी बने लेकिन मैकेनिज्म सेम रहती है. जहां पे OH लगाया है ना, जहां पे OH आता है वहां पे हैलोजन आ जाएगा. हाँ यानी एक कायरल है इसलिए. सी मैं क्या बोल रहा था कि यहां पे अगर हम वाटर की जगह पर हम पूरा ये नहीं करें और अगर हम HBr ले ले, कुछ भी नहीं ले और यहां से HBr से शुरू करें तो यही होगा प्रोडक्ट, लेकिन यहां पे OH की जगह पर Br आएगा. दैट इज व्हाट यू डोंट put 2 of them, 1, right? Okay, and this is going to be a chiral structure, and if it is going to be a chiral structure, then we shall get dextro and levo, both. Clear? This reaction is done in 2 steps. The first step is called hydroboration and the second step is called oxidation. So let us understand how this can be done. The process is very simple. Suppose we start with an unsymmetrical alkene. So, yeah. This is, let's say, an unsymmetrical alkene, CH, double bond CH2. Double bond is like this. Is that okay? I've just drawn a double bond like this. Okay. Now, I take PH3, which is called a borane. PH3, which is called a borane. And borane has an empty orbital. Why? Because the octet is not completed. Now, boron needs to complete its octet, and for that it will need to take electrons. So it would be acting like H plus. H plus was in need of electrons. This is also in need of electrons. It needs to complete its octet. But now it is not as intense as H plus. H plus had a positive charge. This doesn't have a positive charge. So what it'll do is, look at this. Now what it does is, it starts getting between that pi cloud. It starts approaching that pi cloud. See, H plus could disturb that pi cloud. It could disturb that pi cloud very easily because it was plus charge. This actually starts going into that electron cloud. Now what happens is, it would finally disturb the electron cloud and break that pi bond. When pi bond breaks, the two electrons of the pi bond would either go with this carbon or with this carbon, right? So ideally, you will have something like this happening. Right. The pi cloud is gone. So now you find that there is this boron with two regular hydrogens, and the third hydrogen is getting broken because this carbon was positive. This carbon was positive. And therefore, boron, the hydrogen of boron, and now the boron has become negative. The boron now has become negative because of this hydrogen, right? It has got some extra electrons. Now what happens is, the electron density of this bond starts shifting towards this carbon. As a result, the carbon which was quite positive receives some electrons and becomes partially positive because it gets some electrons. So from full positive, it becomes partially positive. And boron, which was completely negative, now becomes partially negative. Why? Because some electron density is transferred. Aji to tutyo nathi. The electrons have been shifted. This bond is on the verge of breaking. So the electrons are being shifted towards this carbon. And that is why this happens. There are many ways of representing this structure, so don't worry. There are many ways of representing this structure. You can have more than one ways of representing. I don't put in a transition state, I don't put dots here. It's just to make you all understand how this works, right? It's just a representation. Now what happens is, this bond gets completely formed and this bond gets completely broken. Eventually, you have CH3, CH2, CH2 and BH2. Right? I can put BH2 on the other side. I can have BH2. All okay? After this step is done, boron once again is empty. So what do you expect? One more reaction like that? So it will try to push this once again in the pi cloud. of one more alkene. So, what would happen? I can have one more alkene, CH3, CH double bond CH2 interacting. Now, this step is called hydroboration. If you remember, what has happened? You had your alkene here, CH double bond CH2. This carbon gets what? In the end, the bond is broken, right? This carbon gets what? Hydrogen. And this carbon gets what? Yeah. That is why the step is called hydroboration. One part gets hydrogen, the other part gets boron. So it's hydroboration. And remember one thing, boron, BH3 or BH2 itself is a big structure. So it would want to remain attached with that carbon which doesn't have any groups on it. So that hindrance is less. So now, boron always tries to settle on the carbon with more hydrogens. Because this carbon has one big group attached to it. So boron would not wish to go here. It would want to go here because there are two hydrogens and there is less hindrance. So it's very simple. And therefore, this, right, is one more step that happens now. So now one more thing that is happening here, CH3, CH2, CH2. Now you have P, H, and the other one is CH2, CH2 and CH3. Do you get this? Still one hydrogen left and boron still in the same situation after this step. So one more alkene now. As long as you have hydrogen, that is hydroboration possible. Once the hydrogens are exhausted, hydroboration would not be done. Right? So one more step. Same as through. આમાં થઈ ગયું ને B માંથી એક H અહીંયા ગયો. This was CH2 double bond CH and CH3. So this got H and this got a boron. Same. Look at this, the third one. Pay attention. CH3, CH double bond CH2. Now you will have to put H here and the boron will get attached here. So now what do you get? You get boron with CH2, CH, or I can have a better way of putting it. I can have, because there's less space, I can put CH3, CH2, CH2, boron. I can have CH2, CH2, CH3, and I can have CH2, CH2 and CH3. You still have an empty orbital on boron, and now of no use because there are no hydrogens. So that's the end of the hydroboration part, right? Now, what is this called? This is called a tri-alkyl borane. Instead of alkyl, you can write tripropyl here. Tripropyl borane, right? So this is the first step. Now, okay, once you know this, right? Once you know this, how do you put this when you're asked in the exam? You don't need to explain anything in exam, right? So how do you put it in exam? Exam, what you need to do is a simple thing. 3 times CH3, CH double bond CH2 in presence of B2H6 and THF. THF is a solvent which is used here, and BH3 generally exists in form of B2H6, diborane. It doesn't remain alone, but it reacts alone, right? So it breaks down before it reacts. And now, what do you get? You just need to put CH3, CH2, CH2, 3 times and boron. That's it. Story over. Here. It's a solvent. Tetrahydrofuran is a solvent. A good solvent. चलेगा. Stoichiometry matter नहीं करती यहाँ पे. I could have written B2H6 and from that B2H6 I would have written 2BS3 and from that 2BS3 I would have taken 1BS3.
ऐसे देखा दो बनेंगे
ऐसे organics के अंदर you don't have to worry about the stoichiometry इसीलिए. You don't write the exact thing because you write the form in which BS3 comes to you. BS3 comes to you in form of B2H6. Yes.
सर जो ट्रायड बना उसमें भी तो ऑर्बिटल तो अभी एम्प्टी है.
एम्प्टी है, हम करेंगे ना उसका. लेकिन अब क्या करे, क्या H तो निकलेगा नहीं, तो अंदर जाके भी वापिस आ जा पड़ेगा. कुछ आगे तो होगा नहीं, कार्बोकेटाइन बनेगा, अभी एम्प्टी रहेगा, कुछ और हो ही नहीं सकता. कार्बोकेटाइन जनरेट होगा यहाँ पे जैसे होता है पहले, जैसे ये होगा, पर यहाँ पे कुछ है ही नहीं, H है ही नहीं देने के लिए, तो आगे होगा क्या, तो वो केटाइन तो रहेगा नहीं, तो वापस बोल देगा कि चलो भाई निकलो. That's a reversible process. It has to go back. Huh. So this was the step number 1, which is called hydroboration. Now we go to step number 2, which is called oxidation. Now, oxidation, how would this happen? Right? So, obviously, you take boron, CH2, CH2, CH3, CH2, CH2 and CH3. We're not doing the mechanism, so don't worry. CH2, CH2 and CH3. Okay? This is now treated with H2O2 in alkaline medium. Now there is some rearrangement or whatever it be, don't worry about it. But what happens now is that your H2O2 actually, which is given like this, in presence of base becomes OOH minus. H is pulled out. H2O2 and OH. So H2O2 is this HOOH. Now in presence of base, what would a base do? Pull H plus. So it pulls H plus and you will have O minus here. So O minus, O and OH. And now your boron is going to get this. The boron is going to get this. Clear? When it goes like this, what happens? You find that there is boron with, I'm just putting CH2, CH2, CH3, CH2, CH2, CH3, CH2, CH2, CH3, and now you will have O, O, and H, and this boron would be negative. Do you agree to this now? And now there is going to be a rearrangement taking place. Oxygen-oxygen bond is always very weak. It breaks very easily. So what happens is, there is a lot of electron density here. So electrons are being pushed back. As a result, there is rearrangement. And what kind of rearrangement? Look at this. This connects here and this goes off. So pay attention. This is how the mechanism goes. Now, what do we have here? Instead of having simple alkyl group, now you will have O and then this. And this would still remain as it is, plus OH minus. It is alkaline medium. All okay? Repeat 2 more times. There is enough H2O2 given. So repeat 2 more times. And what do you get? You get B, O, O and O. Trialkoxyborane. Instead of alkyl borane, now you have trialkoxyborane. Boron has entered into, again, the same situation. But now you don't have any alkyl group to even undergo rearrangement. Exhausted. So now in the end, because boron is having a big problem because initially it had only alkyl groups, now you have 3 oxygens around it, making it even more deficient in electrons. Electronegative groups. So now what is the next thing that happens? The next thing that happens is your OH, a lot of OH ions. These OH ions now enter and do the rest. Finally, the alkoxy group is kicked out. So now this happens 3 times. Right? This happens 3 times. And what would happen here? You get alkoxy group. How many? 3 of them. And what else do you get? BOH thrice. The medium is water. The medium is water. An alkoxide would not stay as alkoxide in water. It would pull H from water and convert H into OH minus. And so ideally, I can take this. Ideally, I can put this. This is how you get the alcohol, the final step. Now, you don't have to do all this. It is just that he was asking, and I said like, "Ani pehla hi batch mein mechanism mat kare." This is just that because I was recording, I could even do the mechanism. But now, I will have to give a summary for like, this is just there, but then how do you go about the product? Just as I gave here. The most important step was this. The most important step of the first part was this. Hydroboration is this. Now what is oxidation? So pay attention. I'm going to talk about oxidation. So finally, what do you get in the end? So here you say oxidation. It's CH3, CH2, CH2. This is 3 times with boron, right? 3 times with boron. And we will be using H2O2 with OH minus. I'm doing oxidation. Now pay attention. I'm going to break this bond. All of this is just a disconnection. Boron gets 1 OH and this also gets 1 OH because you've taken H2O2, which produces 2 OH. That's it. So you'll get 3 times CH3, CH2, CH2, OH, and that'd be BOH 3 times. And this is it. Now, so this was so simple, right? Huh? સ્ટેપ છે ના કરી આ રીઅરેન્જમેન્ટ છે મેં લખી છે આ સ્ટેપ જોઈએ છે એ રીઅરેન્જમેન્ટ છે એટલે when you have a peroxide છે એક વખત alkoxy બનાવી દેશે પછી OH goes into it because it's still devoid of its octet and OH would make this negative, and once this becomes negative you find that this would move out taking both the electrons. So this will be O minus and OH goes here. So O minus how many times? 3 times. And O minus cannot remain as O minus. We'll take proton from water. This H comes from water. So water gets converted into OH minus and this H given. That's just do this. Okay, everyone? Is this okay? I think that's more than perfect. And now coming to the important things about hydroboration oxidation. What exactly would happen? Hydroboration oxidation, there are few things that you have to remember. One, it is syn addition. It is syn addition. Two, there are no intermediates, so no rearrangement. And three, you also find that it is anti-Markovnikov addition of water. એવું જરૂરી થોડું છે કોણે એવું કીધું હતું કે મોસ્ટલી ના હોય બહુ બધી જગ્યાએ ફ્રી છે એ જરૂરી નથી. Okay, I'll give you an example where you have anti-Markovnikov in ionic mechanism. જે તું કરે છે કાર્બોકેટાઇન mechanism એમાં જ anti-Markovnikov કરે. એમાં ને એમાં જ બતાવો. ના એ જરૂરી નથી. એટલે તમે જે કન્વેન્શનલ રિએક્શન્સ આપણે કરીએ છીએ જ છે, પણ એવું જરૂરી નથી કે દર વખતે એનું એ જ થાય. એટલે બતાવું છું હમણાં. આટલી ખબર પડી ગઈ બરાબર? Is that okay? Imagine if you have something like this. This is just out of curiosity, someone asked, look at this. Now, where would you put your positive charge? Here? This is a nitro group. It is one of the strongest, very strong electron withdrawing group. Now, if you put your positive charge here, and if this group is going to withdraw electrons, what would happen to this positive charge? It will get even more intense. The magnitude of positive charge increases. If magnitude of charge on any atom increases, the structure gets destabilized further. The system would not allow this to happen. So here, I cannot put a positive charge close to NO2. I will have to put my positive charge away from NO2. So in that case, I would say here, NO2, forget your rules, right? Save the cation, make it stable. So that's how it is. So CH2, CH2. So positive charge now taken by the first carbon, CH2Cl. That's your major product. Now this is anti-Markovnikov. It still follows cation mechanism. She cannot generalize anything. You have to know a lot of things, right? Okay, so this was just out of track. So let us take this away and just put this away. Let us take this here. So now what is your product? Finally, What is your product? It's a propanol. So pay attention. Now if I have to give the full reaction, how do I give that reaction? CH3, CH, double bond CH2 with, or I can directly put, first step, just a moment. So here we put B2H6 and THF, and 2 we put H2O2, oxidation, and OH minus. So what we do is we get CH3, CH2, CH2 and OH. Let us put this aside. All right, and this will be like 3 times. This will be 3 times, and this will be BOH thrice. Now, if you closely observe, hydrogen has been added here, and OH has gone here. All okay? So that's anti-Markovnikov. Okay? Now, if you take up this now, once again the same old thing, right? And if you perform the same reaction as given here, 1 B2H6 and THF, and 2 H2O2 and OH minus, what we get is one side gets H, the other side gets OH. So you can put both of them on wedge or both of them on dash. Doesn't make any difference. All okay? Clear? So this is how it goes. All okay? Clear? So 3 things here. Syn addition, no rearrangements, anti-Markovnikov addition of water. Now here, if you properly understand, where did this H come from? Where did this H come from? This H came from BH3. And where did this OH come from? From H2O2. Finally, from H2O2 as such. Right? So here, you have to remember that H comes from BH3 and OH comes from that system of H2O2 and water. Right? Okay. I think this is important. I hope everyone has understood this. Should not be a problem, right? Okay. The third reaction from alkenes that we take up now. The third reaction is an extra reaction. It's called Oxymerculation and demercuration. Oxymerculation and demercuration. So let us understand what this oxymerculation and demercuration is. This is extra and not given in our textbook, but we just need to understand how the reaction goes. Again, if you take an unsymmetrical alkene, right, and we perform 2 steps. First step is addition of HgOAc twice. This is called oxymerculation. Now, OAc, what is OAc? AC here would be COCH3. That's AC. Yeah, acetate group. Acetyl group, I'm sorry. OAC is acetate group. So this is what you have. Now, this is step number 1. And step number 2 is demercuration, which is done by using sodium borohydride. And this would give you CH3, CHOH and CH3. So you need to remember the conditions. I'm not giving you the mechanism here once again. Not needed. But important things that you have to remember would be like anti-addition of water to, you will have no rearrangements, and 3, so it's anti-addition of water, there would not be any rearrangements, and it would be like Markovnikov addition. So the basic difference between the two reactions was, here there is Markovnikov addition without rearrangements, and when you add water in presence of acid, it is again Markovnikov addition but with rearrangement. And hydroboration oxidation is anti-Markovnikov addition without rearrangement. So rearrangements occur only when you add acid in presence of water. Acidic hydration, there is rearrangement and Markovnikov. For remaining two, there is no rearrangement. HBO, that's hydroboration oxidation, is anti-Markovnikov addition, and oxymerculation, demercuration is Markovnikov addition without rearrangements in both of them. Okay, all of you?
सर पिछले रिएक्शन इसमें जैसे दोनों में स्पीड कैसे डिपेंड है जैसे कार्बोकैटायन रिएक्शंस में तो क्या होता है कि कार्बोकैटायन की स्टेबिलिटी पे स्पीड डिपेंड करती है.
So let us try and revise all the three methods. This is a question where you revise all the three methods and where you find that all the three products are different. The first one here, look at this. Acidic hydration. What do? Markovnikov with rearrangement. So let us begin. All of you all start writing. You can do this. All right. So first of all, you start with CH3, C, CH3, CH3, CH, double bond CH2, in which we take up H plus and H2O. Now, if this is the first thing, you get CH3, C, CH3, CH3, CH, CH3 and plus. All okay? What kind of carbocation is this? Secondary. Is there any possibility of making it better? Just look at this carbon here, quaternary carbon. Shift it. How? By taking one of the methyls and putting it here. This is then called, what do you call this? Methyl shift. Now this methyl shift would be something like this. CH, CH3, and then once again you will have CH3. Okay? And now you put your water. So plus H2O, you put plus H2O, you add water, and minus H plus. What do you get? CH3, COH, CH3, CH, CH3 and CH3. Right? And this is your A. I hope you've understood what A is. Clear? Now we start taking B. હા હવે બી તો સીધું છે, બી ને સી તો સીધું, આમાં બી સીધું કરશો તો વાંધો નથી. Now this was the first one. All right, the second one goes here. CH3, C, CH3, CH3. Now the second one is hydroboration oxidation, right? So what would be anti-Markovnikov addition of water? So if anti-Markovnikov, hydrogen gets added here and OH here without any rearrangement. So I'm just putting the answer. This is going to be your B. And what is going to be your C? What is it? Markovnikov without rearrangement. Okay, that's correct. So C would be like your CH3, C, CH3, CH3, CH, OH and CH3. That's the C part. I think this is about the full thing, right? Okay. So this is one more preparation, right? Carbonyl compounds. Carbonyl compounds that we have are aldehydes and ketones. So we talk about how to reduce aldehydes and ketones first. Yeah, first of all, when you reduce aldehyde or a ketone, for example, when you take the simplest of all aldehydes, that's methanol. You can use any one of these reducing systems. So for aldehydes and ketones, the reducing systems possible are reduced to alcohols by, you can have one system NaBH4 or LiAlH4. The second way of doing this would be using catalytic hydrogenation, H2 plus Ni or PT or PD. Anyone. Here you have, the reactions are more difficult, so a little more extreme conditions. High temperature and pressure. And the third method that you can use here is a system of Na plus ethanol, sodium plus alcohol. And here aldehydes and ketones, they can be converted into corresponding alcohols. Starting with methanol, formaldehyde, I can take up LiAlH4 or NaBH4, anything. This is first step, and in second step I need to put H3O plus hydrolysis. This would give one hydrogen here. You have to break this pi bond, give one hydrogen here and one hydrogen here. So ideally you get H, C, OH, H. This is methanol. Right? What exactly happens here when you take lithium aluminum hydride or sodium borohydride? What exactly is happening here? It's like your aldehyde or ketone, whatever it be, when treated with a borohydride or an aluminium hydride, it is something like this. B minus Na plus. This is your borohydride. Here, this is partially positive. And so, hydrogen comes out as H minus. Hydrogen comes out as H minus. It's a hydride ion. And what would happen? You find that this would result into formation of the mechanism I have simplified, and this would further give me in presence of H plus, I have my alcohol done. All good? So this is how it works.
Sir, આની અંદર આપણે comparatively જોઈએ તો LiAlH
સમજાવું છું, સમજો, બધું સમજો. એ જે આવે છે, the comparative part and everything. Just understand the mechanism. હજી તો વાત છે.
सर ये Na प्लस की जगह H प्लस कैसे
Huh?
Na प्लस जो ऊपर है उसमें H प्लस कैसे लगा उस आखिरी स्टेप में?
This is an ionic structure. This is ionic structure. तो जब भी हम H plus डालेंगे ना, it makes a covalent bond which doesn't come off. तो इन्हें तो छूटा अलग ही होता है. Thank you. All right. Now coming back to this, methanol forms methanol. Now you take any aldehyde in the same manner. Or a ketone. Do the same reaction. 1 NaBH4 or LiAlH4, and 2 it is H3O plus. In that case, I directly put the product now. RCHOH and then H or R. What I have to do is like give one H to this carbon and one H to this oxygen and break this bond. That's it. Now if you take an aldehyde, there would be RCH2OH. So it will be a primary alcohol. And if you take a ketone, this H would be replaced by R, so it will be a secondary alcohol. So I can say aldehydes except HCHO. You know that methanol gives methanol. Methanol gives methanol. So all aldehydes except HCHO would give you primary alcohols. And all ketones would give you secondary alcohols. All good? So this is how it goes. Now, once this is done, I would give you the reactivity and the selectivity. First of all, if we talk about sodium borohydride and lithium aluminium hydride, both of them are able to react in the same manner as it seems. But remember, lithium aluminium hydride is much stronger in its action as compared to sodium borohydride. And hence, there are, apart from aldehydes and ketones, which are reduced by both sodium borohydride and lithium aluminium hydride. Right? Apart from that, lithium aluminium hydride is also able to reduce quite a few other groups which are not reduced by sodium borohydride. In fact, I can give you a very simple comparison between the other reducing agents. For example, let us talk about something like this with a pi bond. Now, if I use LiAlH4 or NaBH4 and H plus, this is a ketone. So what we get is the double bond remains intact. So one part gets H, the other part gets OH. H and OH, right? So it's like one H here and one H here, the double bond breaks, and you have a secondary alcohol formed. However, the same reaction you try to attempt with H2 plus Ni. Here you just write high temperature and pressure. And what you get is this. The only difference is even the C double bond C is reduced. So you need to know that lithium aluminum hydride or sodium borohydride as well as sodium and ethanol, they are very similar in their actions and they would not affect C double bond C. Whereas if you take H2 and Ni or any other catalytic system, you have the double bond also reduced. So that's the difference between the two. One more thing here. If you have a system like this with COOH here, remember, if you take NaBH4 and H plus, the product is going to be this. HNOH, a secondary alcohol. COOH doesn't get affected. You take LiAl, H4 and H plus. In that case, you have OH and H, and then you will have here CH2OH. Even the acid is reduced to an alcohol. So lithium, so I can say lithium aluminum hydride can reduces COOH groups, COOR groups, apart from the aldehydes and ketones. It also reduces CN group. It also reduces CONH2 group. And it also reduces COCl group. These are some of the common groups which are reduced by lithium aluminum hydride. But talk about NaBH4. It mainly reduces aldehydes or ketones and acid chlorides, COCl. These are the two groups which are primarily reduced by sodium borohydride. I would now show you how acids and esters, they can be converted into corresponding alcohols by reduction. I've talked about aldehydes and ketones being reduced by sodium borohydride and lithium aluminum hydride. Now I would talk about how acids and esters can be reduced in the same manner to alcohols. Now let us understand the second part. How do you reduce acids to corresponding alcohols? So we are trying to attempt this reaction, RCOOH to be converted to RCH2OH. RCOOH becoming RCH2OH. So here we take up we take up lithium aluminium hydride. That's possible. And then H plus. Or you can take up B2H6 in THF. In fact, B2H6 is one such reagent which is specialized for reduction of acids. So, very selective in its reduction, will not affect most of the other functional groups. So it's very selective in its approach. The next thing that we have is, like, I can give you a specific example for doing this. You can have, let's say, an aromatic acid like benzoic acid. And if you use lithium aluminium hydride and then acidify it, what do you get? You get CH2OH plus H2O. One oxygen comes out as water. So this is the second part where I have reduced carboxylic acid and you get a corresponding alcohol. It has the same number of carbons as the carboxylic acids. No change. Right? It is just that one oxygen replaced by two hydrogens. Take out one oxygen and put two hydrogens, and that's it. Do you figure that out? Now, the third is reduction of esters. So now, when you try to reduce esters, so now we go back to reduction of esters to alcohols, right? So now any ester, R, C double bond O and OR dash. This is an ester. When you reduce it, generally it splits up into two parts. The first part becomes RCH2OH, that's an alcohol. And the second part would become R-OH, which is another alcohol. So overall, you have two alcohols formed, right? One from the alkoxy group and one from the carbonyl, right? So now, how do you do this is very important. So we have the first reducing system, which is like lithium aluminium hydride, which is always there. Second is sodium plus ethanol, which is also very effective. And third is the most important method. It is H2 plus catalyst. This catalyst that they use is CuCr2O4. It's a very important catalyst and not very costly. It is a cheap catalyst. And hence, it is more effectively used. So ideally, things like lithium aluminium hydride, which are actually very costly, they can be avoided. So even when you have to reduce a carboxylic acid to an alcohol, You don't use lithium aluminum hydride or diborane. These are both very, very costly reducing agents. So on an industrial scale, what you need to do is like you convert that acid into an ester first by reacting it with alcohol. There's this H plus catalyst. Water is lost, you know that? Esterification. Water is lost, alcohol loses H, acid loses OH, and it's a condensation reaction. R, C double bond O, OR dash plus H2O. This kind of esterification is done, and this esterification would convert your acid into an ester, and now this is reduced by catalytic hydrogenation, where the catalyst uses CuCr2O4. This is a very simple way of doing reduction, very easy, and that is why it is preferred to convert acids into esters, and then these esters are further reduced by catalytic hydrogenation. Clear? The last method now that we have for our curriculum is getting alcohols from Grignard reagents. So let us take up the last method, not a very difficult thing, very easy. We can do this very, very fast. First of all, you can react different carbonyl compounds with Grignard and get corresponding alcohols. That's the thing, right? So how do you start with this? So you can take a simple carbonyl compound. The simplest is something like methanol. And you can take, let's say, a methyl magnesium halide. If you do this, you will have minus and plus here. This is also partially positive. So the minus part goes here, and you can have HCO minus MgBr plus, neutralizing it, and then you'll have H and CH3. And now when you put H plus here, you will have H, C, OH, CH3 and H. What do you get? You get CH3, CH2, OH. What do you get? CH3, CH2, OH. Clear? So this CH3, CH2, OH, if you look at this CH3 and then CH2, OH, pay attention. By reacting methanol with a Grignard, what have you added to that Grignard? CH2OH. This is a Grignard. What do you think? Yeah, when you react this with Grignard, what has been added here to CH3? So that's CH2OH, right? So this CH2OH is basically what? It comes from methanol. And this is the part coming from the Grignard thing. Sorry. This is something which comes from Grignard. So ideally, what I want to make you all understand is, if you want to add CH2OH to any alkyl group, if you want to add CH2OH to any alkyl group, just take methanol and a corresponding Grignard and do the reaction. For example, coming back to this, Suppose if I want to have this, I want to have benzyl alcohol. What should I do? I should take methanol, which would give CH2OH, and what else? I need to take phenyl magnesium bromide. So what would happen then? This is the negative part, right? So this negative bond would connect here, and you will have C, and then that'd be HO minus MgBr plus. And if I acidify this, put a proton to it, I'm going to get my CH2OH. So any primary alcohol can be obtained by reacting methanol with a corresponding Grignard reagent. Yes. Good? All right. So this was one. So what do you come to know about it? You say that if you want to get a primary alcohol, you have to take methanol and react it with a Grignard. Okay. Now if you generalize this for any other aldehyde or a ketone, any other aldehyde is this, or a ketone is this. Any other aldehyde or a ketone, if I take a Grignard RMGX, this is partially negative, partially positive. So this R goes here, this goes up, and you have this R, C, O minus, MgX plus, and then we have this H or R, and this is going to be R dash. And now, when I put H plus here, I get the corresponding alcohol. So I get OH, I get R dash, I get H or R. So if I take a ketone, what kind of alcohol am I going to get? If I take a ketone, there would be a tertiary alcohol because there would not be any H here. If I take an aldehyde, it will be a secondary alcohol. So in general, what do I say? I say, let us generalize this. Methanol gives primary alcohol. Any aldehyde except methanol would give you a secondary alcohol, and ketones would give you a tertiary alcohol. So primary, secondary, and tertiary. This is what. All good with aldehydes and ketones, how they form alcohols? Okay, coming back to what else could we probably use here. So, there are some compounds which react with Grignard in a very similar manner and would produce alcohols. Now, which are these compounds? This is one of them. OR dash. What is this? Ester. What is so special about an ester? It has what? What is this? A leaving group? Do you know anything else which has a leaving group like that? Very good. I can put Cl. What is this? An acid chloride? RCOCl? And where is your leaving group? It's here. Do we have anything else? Maybe this? What is this? Where you have, instead of having OR dash, you have OCOR dash. That's an anhydride, and anhydrides also have a kind of leaving group. This is also the leaving group. So there are three other molecules which have leaving group, and they all react in a very similar manner with Grignard. I would give you the reaction for one, and you can understand how the rest of them react. It's the same way. Okay, so let us start with how these three react with Grignard. I'm taking the example of an ester, and I'm putting a Grignard here, CH3MgBr. This is minus delta, this is plus delta. The first reaction, and you have R, C, O minus, MgBr plus OR dash and CH3. Now when you have a leaving group, the pi bond which is broken gets reformed and leaving group leaves. So what do you get? C double bond O and then CH3. Now in such reactions, if below Grignard, if they write one equivalent, the reaction stops here. Now this may be the same fate. So what you get along with this is like plus MgBr OR dash, right? If I would have taken acid chloride, instead of OR dash, I would have got Cl. And if I would have taken anhydride, I would have got OCOR dash. But the rest would remain the same. They are all leaving groups. They do the same thing. And now, what else? Pay attention. Now your ketone is going to react further let me put it like this, CH3 MgBr. This is, you know that this is negative and this is partially positive, so and we find that we have O minus MgBr plus CH3, one more CH3, and now protonation, which gives me my tertiary alcohol. So now you get a tertiary alcohol with an ester, acid chloride or acid anhydride when you react them with Grignard. Why? Because the first product formed is a ketone, and ketones always give tertiary alcohols. All okay here? Preparation of phenol, the first preparation. This preparation is from chlorobenzene. This preparation is from chlorobenzene, and the method, it is an industrial process which is called Dow's process. The reaction, as it seems, is very difficult because you are taking chlorobenzene and trying to do something which is so difficult on an aryl halide. Which reaction is very difficult on aryl halide? Tell me. What is the most difficult thing on aryl halide? SNAR. This is one of the most difficult things. So now just understand the conditions. We're taking aqueous NaOH and we're going to keep a very high temperature of 623 kelvins and 300 atm of pressure. All this would give us the first product. Because we have alkaline conditions, we cannot have OH formed, but it will remain in O minus and Na plus form. This is going to be, what is this called? This is called sodium phenoxide. This sodium phenoxide can be acidified, and when you acidify it, you will get OH, that's phenol. So from chlorobenzene, you can get phenol. This is the first process. Now this is an industrial process, very difficult because it is an SNAR type of reaction. Now, in this process, there is one very typical byproduct which is always formed. Now, what is the byproduct involved here? See, at the first stage, where you get this O minus and Na plus, at this point, you can have some unreacted chlorobenzene, which is still in the process of getting reacted. You can have some of this reacting further and forming something like this. Which is called diphenyl ether. This is one of the major byproducts involved in in this process. So this is a byproduct that everyone should know about. This is the byproduct of the whole process. Sorry. Putting it separately. So I think this is the first process, and I hope you've understood this. The next process goes from chlorobenzene to benzene sulfonic acid. So from benzene sulfonic acid. Again, a process which is so important. Here, we start with benzene. And we can take oleum. Oleum is nothing but H2SO4 plus SO3. Or we can put it as H2S2O7 oleum. And this would give you an electrophilic substitution reaction where one of the hydrogens will get replaced by SO3H. And what you get here is called benzene sulfonic acid. This is your benzene sulfonic acid. This benzene sulfonic acid now undergoes a very typical reaction. This reaction is called caustic fusion. And how would that happen? You have to take NaOH solid and heat it. The reaction has a special name, as I've told you. This is called caustic fusion. And this caustic fusion is going to give you, and this caustic fusion can be followed by acidification, so that I don't have to write two things. I can directly write OH, and that's phenol. Right? So this is again the second way by which you can make your phenol. The third method that we can talk about is from benzene diazonium chloride. So what do you get from benzene diazonium chloride? This benzene diazonium chloride, you have this aniline. What do you call this? Aniline. And aniline is subjected to a very important process, which is like NaNO2 plus HCl. This is done at 273 to 278 kelvins, and the process is called diazotization. And this will give us an intermediate, which is N2 plus and Cl minus. This is what we call as PDC. What you have here, PDC, benzene diazonium chloride. This benzene diazonium chloride can be treated with either dilute H2SO4, simple, or you can have H2O and then heat. So heat it a little. When the temperature reaches about 10 degrees Celsius, the reaction starts happening, and you will see effervescence of nitrogen gas coming out. So what you get is this plus N2. This is phenol. What you get here is phenol. And the reaction has a special name. It is called hydrolysis. So this here is hydrolysis. This one was diazotization. Yeah? So this is your third way of getting phenol. Hydrolysis of benzene diazonium chloride, as they call it. All okay? The fourth method and the last one. The last process is called the cumin process. So what do you do in this process? Let us take up that. In cumin's process, what we do is we try to make cumin, but let's say this is cumin first of all. CH3, CH3. This can be called cumin or isopropyl benzene or bracket this is 1 and this is 2, so it is 1 methyl ethyl. This is 1 methyl ethyl. We are taking it as a complex substituent, and then benzene. Right? So these are all different names of the same thing, cumin. So ideally, टू बेंजाइल नहीं, टू फिनाइल बोल सकते हो, लेकिन वो भी नहीं हो सकता बिकॉज योर पेरेंट चेन इज अ बेंजीन रिंग, सो यू कैन नॉट पुट इट लाइक दैट. કરી શકાય, બહુ વાંધો નથી, પણ I would suggest do it. Do write one. Right? But the point is this, how would it react? So let us take this and react it with air. Air is nothing but O2. And this would result into giving us a very unique intermediate. You will have CH3 remaining as it is, but between C and H you will have oxygen inserted. This is called cumin hydroperoxide. And this may undergo rearrangement when you add a little bit of acid into it. So with a little bit of acid, dilute acid added, there is some rearrangement taking place. So what happens in the rearrangement? This bond shifts here and connects with this, and this bond shifts here. So you find that your benzene ring gets OH, and this part here becomes CH3, C double bond O, and CH3. This is a byproduct which is acetone. It is a very useful byproduct which makes this process very, very important. Cumin process is one of the processes by which a lot of, a big production of phenol is carried out. So this is very good process. Byproducts are also important. Now, it's just about, I need to talk about how you get cumin. How do you make cumin? That's something which is not given in textbook. But you need to know that because they normally ask you the full, the full reaction. But because they know that you have to know this because you've done electrophilic substitution reaction. All right. So one of the easiest way of getting cumin would be, because it is alkylation, let's take benzene and let's take CH3, CH, Cl, CH3, and we take anhydrous AlCl3, and let's see what happens. Because of this, what reaction happens? You get CH3, CH, CH3, and Cl plus AlCl3. What do you think you get? You get CH3, CH, CH3 plus, let me put plus here, plus AlCl4 minus. This is your electrophile that you generate. And now this electrophile gets onto that ring and you get cumene, right? CH, CH3 and CH3. This is one way of getting cumene. Now, you could probably have another route. You could probably take CH3, CH2, CH2 and Cl and anhydrous AlCl3. But you might think this will not give us cumene. It'll give us what? Propyl benzene, not isopropyl benzene. Let's understand why so. CH3, CH2, CH2 and Cl plus AlCl3 gives you, what would it give you? CH3, CH2, CH2 plus AlCl4 minus. This is, however, primary, very good, and this is going to undergo hydride shift. Why? Because the carbon next to it is secondary. So you can have CH3, CH plus and CH3. This is a secondary. So ideally, you will, let's see, ideally, what would you get here? You would once again get the same thing. Cumene. All okay? One more way of getting it. 3 ways have been described so far. One more way of getting it. You take CH3, CH double bond CH2 plus H3PO4 and the temperature is 523 kelvins. So what would happen here? CH3 gets protonated. CH3, CH double bond CH2 gets protonated because of the acid. So what would happen when it gets protonated? You get CH3, CH plus and CH3. H gets added here by Markovnikov and there's a positive charge created here. So it would once again give you the same product. Cumene. So either way, you get the same product. Whatever you do, you're going to get the same product. I hope you've understood this. 3 different ways of getting the same cumene, right? And that cumene can be converted into phenol, right? So that ends the preparation of phenol and alcohol.